Hello, everybody. So, got a couple things to talk about today. Should be shorter than Monday's class. That should be the last really long one like that. And our general schedule now, the rough plan for the rest of the semester has us to our general schedule every day, where we go for about an hour and 10 minutes, take a break, then another hour and 10 minutes, and then the rest of it will be lab time. So that
I have a question.
should be the last two break day. Yeah, what's that?
So one of my questions is, so for the due dates Saturday, will it be every Saturday now? From now
No,
on?
just this week.
Okay.
Yeah, that's just for this week, since we didn't cover that material until Monday. But yeah, we should be back on track now. This module just had more material to cover.
Yeah, it's just that, next week, like, it's just like, Wednesday. So it's just like a Saturday, everything. Then Wednesday. So everything is just kind of just crammed in there. So.
Yeah, we should cover. There should be plenty of time for the rest of the stuff, though.
Okay, that's good.
Normal
at least we have time for everything to be covered. So.
Yeah, that module 3 had several of our major course learning objectives all at once, which is why Monday's class went so long, because we had to fit those in there. Today should be a little bit shorter. Some content stuff to start off with. I split the stuff about logic up into 2 lectures. We'll start into that today. Just kind of talking about logic and the idea of what it is, really why that word shows up in so many of our classes, because you've probably heard it in other places than just the name of our course here. Then we'll get into the logical operators, the ones we'll use to the ones we're used to working with. Oh, a comment in the chat room about those Wednesday due dates. Yeah, remember that our schedule we went with the schedule where the module stuff is due before the next module starts, which the semester this week goes from Wednesday to Tuesday. So our due dates are in the middle of the week, which is also should allow time to ask questions about homework before it's due. So we have Monday to ask questions. Most people are going to do homework on the weekends, and then Monday is a good time to address questions for that. But for today's agenda, got some stuff about logic, and I split it up into 2 sections where we have just the general overview of logic as a total subject, and then the logical operators, which, depending on what the time looks like, we might push that back till Monday. Because there was a whole lot of talk on Monday, so I figure y'all are ready to do something. So I'm going to get into an example. So we'll go over some random numbers and do random numbers and go through a class example programming things today. That way we're more actively doing the fun part, and then the talking part split in half. So some of the half of the talking part got pushed back till next Monday, and then we can do stuff, the fun part today. Does anybody have any other questions before we get started? I know there was a couple show up there. Okay, I assume the silence means no questions. Oh, one other announcement. The computer club, which is going to be renamed the Tech Club. There was some talk about that. Had a meeting yesterday and decided on a few things about upcoming events and some stuff for the club to do. And then this morning I created an Ivy Learn group thing to have a nice official channel for that. So for all of those here in the IT program, remember there is a club where you can actively do stuff, and some fun events coming up that were discussed at yesterday's meeting, but Tyler is involved in that. Your classmate Tyler can fill you in on a lot of the club details if you're curious about that, or when our next meeting might be scheduled and stuff. So I guess just be aware of that.
We plan on it next Tuesday around 5.
Okay, yeah, we'll have regular meetings. The club will have regular meetings. I keep saying we. I'm there for administrative reasons, the administrative side of it. It's y'all's club. One event that was discussed yesterday is some a game jam coming up, sort of an end of semester way to relax. Everybody gathers and plays games for a few hours, have some prizes and stuff, but more details on that to come. So now on to the lecture part. So the next couple lectures, because I decided to split this up so we could actively do something for a little while, are going to be about logic. Right? What's the name of our course here? It's computing logic. At one point, it had logic in the name, intro to logic or something like that, and then they changed the name of this course to computer math, and all of the content was exactly the same. All they did was change the name, but when they changed it to that other name, people did not do as well in it. Something about that word makes people panic a lot, so they went back to the older name, computing logic, and people seem to do much better in the course again. Just something about that word causes panic for some people. But the second part of that, the course name, logic. This isn't the only course where that word shows up, right? You hear it in your English classes, your philosophy classes, legal classes, legal studies, math classes. Obviously, it's in IT. That's the name of our course here. And many, many more courses in between. It kind of seems like a variety of subjects like that. It's so separated that surely that word has lots of meanings. Right? It must mean lots of different things if the English people and the philosophy people and the math people and everybody can use, and tech people, we can all use that same word. It must mean a whole bunch of different things, right? Hopefully you very quickly realize there that the simple fact that I asked that question means the logical answer to it has to be no. That question would not have been asked unless the answer the answer is no. It means the same thing to everybody. So a little preview of logic right there, just showing up in normal conversational English. And understanding this is critical for what we're studying here. Well, like I just said, it means the same thing across all these different fields. And in our modern world, all of these different fields do make use of technology, right? So as the technology people, especially as programmers, software development, the other label on our course here, especially along that way, we're the ones that have to tie logic together from what it means back to what that core meaning that's the same everywhere, to tie these fields together. They're all going to use the same technology. So that's why we want to look at logic specifically. So the definition of logic is premise that leads to or results in a conclusion. And both of those words can be plural. We're going to have premises, more than one premise, more than one observation of facts that result in the same conclusion, or multiple conclusions, but we're introducing the topic here, so we'll do it in singular form, and then the plural should follow obviously from that. So that's the definition of logic as it applies everywhere. A premise leads to or results in a conclusion. Let's start with it's English or philosophy class, some sort of language. I'll just put language. Some of our language courses, because I guess it would apply in foreign languages as well, but where we're speaking to each other, or philosophy where we're trying to build deeper understanding of things. We might have a premise like this, and this is the one I'm going to use for our examples here. So I am going to ask for a little bit of leeway in this statement to keep the example simple. I'll use this same case, and obviously the very nature of deciding things like a premise could be debated at length, but let's go ahead and take the premise I'm getting ready to write here as true. That way it'll work for our example. So to keep our example simple, please give me a little bit of leeway with the truth value on this particular premise conclusion set. So a premise might be, it is raining. Oh, that part's a statement of fact, right? And we're going to talk about, when we judge these things, we want to consider truth of value. That's either true or false. It's not good or bad. You know, could really enjoy the rain, or you could really dislike the rain. You could have a bunch of things the rain's preventing you from doing, or a bunch of things that you didn't want to do that the rain gives you an excuse to delay for. So the quality of that true or false, whether that's a good thing or bad, that's a separate issue. But that would be a true or false fact that we could just make a statement about. It is either raining or it's not raining. So that's the premise we have. And the conclusion drawn from that, which this is where I was asking for a little bit of leeway for the purposes of writing out our example. I'm going to say need an umbrella. So you can see, obviously that one could be taken different ways, right? There's other types of rain gear, raincoats, galoshes, all sorts of other things, but please just allow me a little bit of leeway to keep our example from getting too complicated or diving too much into that. If you need, I guess a generalization of it is that represents, we need to react to the rain. We need to do something to keep ourselves dry. But there's a premise, a statement of fact about something, in this case, the weather. And that statement of fact leads to a conclusion, leads naturally to a conclusion, something that in this case needs done because of that fact. Or we might have math. So another example, right, from math, the other extreme end of where the word logic shows up all the time, right? Even in your English class constantly, your English teacher is going to, when your English teacher grades your essays, they're going to have a rubric, and one of the points on there is going to be the Greek word for logic, logos. So it's directly applied there. In your English class, you're going to hear them use that word all the time in lectures. Math class is the same thing. You're going to hear the word logic show up all the time in lectures. And it seems like it might be something entirely different, but the details are different. Our core definition of what logic is the same. So for example, let's look at transitivity here. One of our very important concepts in mathematics. And I'm going to start abbreviating because for these notes, premise and conclusion are going to be written on the board a lot. So I'm just going to write P and C. Kind of easy to tell which one goes with which. For transitivity, we might have a premise something like X is less than Y and Y is less than Z. So a statement of fact, we have a couple of numbers. So we can draw a conclusion naturally from this fact about the numbers we have. And by transitivity, that means our inequality in this case, the less than translates through. So X is less than Y and Y is less than Z. And that's how we know X is going to be less than Z. If you want some hard numbers to put in there, like X is 1 and Y is 2, 1 smaller than 2, and 2 is smaller than 3. So transitivity is the math fact of how we know that 1 is smaller than 3. The formal statement of that, but usually we use the formal statement in more complicated situations. List here. But you can see that it follows that same pattern. A premise, some statement of fact that we know, or that we're at least fairly certain is a fact. One of the things here is about how we can check that and figure out for certain if the thing we're looking at is a fact or just kind of we're getting the illusion that it's a fact. But some sort of statement like that is a premise, and it leads naturally to a conclusion. So whether we're in our English class, our math class, or our AP class, this definition of logic is what applies across the board. It means the same thing everywhere. This is what Star Trek was always being.
Yeah, like Spock.
What's different here? Yeah, this is the logic that Spock was always talking about. It's a statement of fact, and we can support. So in the case of language here, the idea that we need an umbrella can be supported by the facts at hand. The premise leads to the conclusion. So it's a way of proving things and feeling certain, being certain about the things we think we know. And you'll notice that that definition is what holds everywhere across the board. That's why we hear logic in so many classes, because it's a way to be certain about the things we know. And whatever subject we're in, we want to be certain about it, whether we're in a language one or a math one. And I chose those examples for a reason that we'll lead into before long. But you can see if we take that general sense, the premise leads to or results in a conclusion. We have that everywhere, and what changes is the details. For your English class or philosophy class, you need some word-based statement. In your math class, some numerical or equality, inequality sort of statement. But the same general flow from a premise to a conclusion is constant everywhere. And that's what logic is, the flow, that flow from a premise to a conclusion. And further, you'll notice I've already used the words a couple times, that what we're talking about here are always going to be true or false things, right? In this math case, X is smaller. I'll erase those example numbers. So arbitrary numbers that we don't know what they are could be, so just sort of random numbers. But if this one holds true, then this one will be true. And likewise, if this one is false, then this one is false. Same thing in language. If this statement is true, then this one's true. And for the language ones, please a little bit of leeway. Let's take this to be true so our example stays simple. Obviously that could be debated at length, but we'll say one way to phrase, we need to do something about the room. So if this statement is true, then this one's true. Or the other way around, if this one's false, then this one's false. So we're talking about true or false things, which gives us a binary state system. And we have operations that we can do to combine binary states things. In particular, one of them is already up here. And we can have multiple true things.
And you know what I like about logic? And I'm just gonna, not ask a question here, but just, the reason why I like logic is because, there's a premise and there's always will be a conclusion.
Yes.
It'll be either true or false. And so, that's what I just like about logic so much.
Yes, yes. Every once in a while, when it gets really complicated, our conclusion is sometimes we end up with conclusions we don't want, like unknown or
Yeah, but
information. In general, it does follow that flow. Yeah,
and some conclusions we will not like, and but guess what? It's the truth. And so when it comes to math equations or any type of equations that scenarios of a premise, there will be a way to get the conclusions.
Mhm. And we want to say truth value, because sometimes false is what we want. Right? We don't always want the true side, but we want one or the other.
Some people just want
Just
want the false value. Some just want things to be true, and so it's just kind of like that conundrum or that ultimatum of like, you either have to choose one or the other.
Exactly. Yeah, because after that, it gets into which one's good and which one's bad, which one's preferable.
And that's the binary. That's the binary way of thinking. If things are good or bad, and that's we have a code for that now. We have the binary code to determine whether the number is on, either it's on or it's off. And so
that's the next step here. So that gives us a binary state system, and we do have operations we can, such as and. That's the second half of the lecture, which might get pushed back to Monday. Something in particular that we'll use in our examples. So it's going to be a longer section of example. And after the previous Monday, I wanted to try to make sure today's lecture didn't run really long, because that one went on and on and on. So we need a short day after that, right? But and some other things, not and or, we can do stuff with those truth values, different ways to combine them. And we already saw that binary states with at least one operation is enough to build a full mathematical system. And that has been done with logic way before the days of machines. So when was it? 1847, George Boole created what's known as Boolean Algebra. And we can take the truth value from these things and a couple of operations to combine those truth values and build a mathematical system that will apply across the board in logic. Which that's probably that one's actually a little bit closer to what the Star Trek example would be with Mr. Spock and things being logical, because then it applies linguistically or philosophically as well as mathematically and ties them together. And then that tying together is the important reason we're going to draw with this. So the first thing I wanted to talk about here is just a general thing about logic with these premises that lead to conclusions. So our examples today are all going to be singular. The plural form follows suit. We just do the same thing multiple times. Using our not operator, negation, that's one of the things we can do, right? If something's true, we can make it false and negate it. Or if something's false, we can take the polar opposite of that. negation would be the technical term, but in computing stuff, we usually just say not. We have two states. If it's not one, then it has to be the other one. It gives us this will provide a way to check our logic and confirm our logic, confirm our certainty about a situation. As far as programming goes, applying this thing directly, anything we'll see in a classroom will not be difficult enough. We'd have to do a check like this. But in the long run, you obviously after you finish your school, you're going to face much harder problems where this might be useful. So hopefully it might be in the back of your mind until then. But at least through school, it will be helpful in your math and your English classes as you put together a logic for an essay. Put together logic for an essay, and you're like, my sentences seem a little wishy-washy here. And if you want to check to make sure your argument is completely sound and solid all the way through, it'll provide a good check for that. Or if you're doing mathematical proofs, like many people first see in geometry class, it can help, a way to help confirm your logic. Just a little check here. Okay, if I erase the board here for the next section. I assume the silence means that's okay. So these two, I did not choose these examples randomly. That's building to something. It seemed like a good point, but hopefully this will make sense in the long run. And this next little trick can be useful anytime we need to apply logic, which, as I already stated, the whole point of this is because logic shows up in about all of our classes. There's not many classes you would, or not many classes you take at college that the word logic is not going to be mentioned at least once. So a couple more times on here, we'll have our first part is the statement. That's our starting point. That's where we're starting. That's the thing, our original logical statement. I guess I could put that in there. It's not just any statement. It's a logical statement. And that's what we just looked at. A premise leads to a conclusion. So I'm going to rewrite those two that we used. So a premise, it's raining. And the conclusion for that is need umbrella. Or yeah, that point could be debated. We need to do something about the rain in order to stay dry. Or the other two logical statements from mathematics, with transitivity, I'm going to switch to equality this time instead of the less than, but the transitivity is still the same. Like if X is equal to Y and Y is equal to Z, then X is equal to Z. Should be very obvious in this case. If we have three different things, we compare two of them. If they're equal, compare the other two and they're equal, then we know that first thing is equal to the third thing. We don't have to make that third comparison. Very important. A small statement, but very important in physics. It's often referred to as the zeroth law of thermodynamics. If we have three objects and these two objects happen to be at the same temperature, maybe they're both settled into room temperature, and a third object, and these two objects happen to be at the same temperature, then we know these two objects are at the same temperature. And when we get into detailed studies of physics, that makes a big difference because temperature, the formal definition, which most people probably never hear until 300 or 400 level physics class, which most people never take, is actually involves entropy. So furthermore, we know that tells us stuff about the entropic state of those items. But if two things are the same temperature, and then we compare two other things and find they're the same temperature, then we know the first thing, then we know that comparison we haven't made yet is going to be the same. That's how equality works. It translates through. If this is equal to this, then that'll translate through any other equality and work the same. So a small statement, but it leads to very profound results. Without it, a lot of things that we know would start to fall apart. So that's our original statement, but we can do things like we can negate it. And when we negate both our premise and conclusion, we end up with what's called the converse. Converse, where we negate the premise and the conclusion both. So as we look at these, and again, that's really ways we want to take this one to be true, so our example doesn't get super complicated, because the linguistic ones can get very, very complicated very quickly, especially when we consider different people would have different habits and use words slightly differently. But if we negate it, well, negation's easy there. If our original premise was it's raining, then our negation of it is it's not raining. And same thing with the conclusion. Need an umbrella becomes do not need an umbrella. What about the truth value on that? If it's not raining,
It's still logical.
Not raining doesn't as smoothly move into don't need an umbrella, right? First example that always pops to my mind is maybe you're doing a cosplay of Penguin from the Batman. And if you're dressing up as a penguin, you better have an umbrella, no matter what the weather's doing, right? So the lack of rain doesn't automatically indicate the lack of need of an umbrella. There are other reasons we could need an umbrella. This doesn't give any time indication, right? It might not be raining now, but it was raining earlier this morning. So anybody that left their house earlier this morning when it was pouring rain would have brought an umbrella with them. And if they don't keep that umbrella with them, they're going to lose it and have to stop and buy another umbrella next time it rains. In short, this one's a little more situational, right? We need to know more details. We don't quite have enough details to assign a definitive truth value to that. What about our math one? Let's see what happens to this if we negate both of them. So again, we'll have a premise and a conclusion. And if we negate these, which I went with equal, so I can just change all these to not equal. X is not equal to Y, and Y is not equal to Z. Well, instead of starting from scratch, just negating our original conclusion, X equals Z becomes X not equal to Z. Can we say anything about the truth value on that one? Sometimes that might be true, right? We have 1, 2, and 3. And 1's not equal to 3. But what if we have 1, 2, and 1? Because 1 is equal to 1. So in that case, it's false. Yeah, so this time we can't definitively say these two are equal like we could when that was our premise. We need more details. We actually need the details. We have to know what numbers those are. So the converse is situational. And that we need the details. We can't just generalize our statement like we could over here where these two things are equal and these two things are equal. Then we don't have to take our third measurement. We know those two things have to be equal because equality translates through. Or here, if it's pouring rain and we don't have an umbrella in hand, we're going to get wet. Or a little bit of leeway on that one, please. So if we don't do something, we're going to get wet. So if we just negate both of them, we really end up with a situation where we just don't have enough details. It's like, well, we can't really answer for certain. We lose that certainty that we should have with logic. But there's another thing we can do with just that negation. So converse. And our third thing is called contra positive. Where we negate both. Negate the premise and the conclusion again, but we also switch the order. So back to our original statement, it's our premise of it's raining. We negate that and make that our conclusion in the contrapositive. It's not raining. And same thing for our original conclusion from our logical statement. If we need an umbrella, then negating that is we do not need an umbrella. What's the truth value on that one look like? As far as certainty, right?
A lot better.
Yeah,
Yeah, it's pretty certain.
because they're like a Batman penguin cosplay from Batman. Maybe it was raining earlier or going to rain later. Maybe that was what you grabbed somebody for a birthday present because last week one of your coworkers came in soaking wet because they didn't have anything to protect them from the rain on their way to work. Different reasons, lots of reasons that we might not need an umbrella. But if that's our original premise, we know for certain that we do not need an umbrella. One of those reasons would be that it's not raining. So that conclusion follows straightforward. And moreover, it has the same truth value. So we took that to be true, that if it's raining, we need an umbrella. So if we don't need an umbrella, it's not raining is a true statement. And part of the reason I wanted to leave this one generalized and debatable is we could also say that's false, right? If it's raining, maybe you don't like carrying umbrellas and you always go with a raincoat instead, which would make that a false one, right? But if that's false, then that one would be false as well. So the logical statement and the contrapositive will always share the same truth value. Whether it's true or false, because those don't confuse true and false with good or bad or preferable or unwanted, and some of the opinionated terms, right? Sometimes false is the one we want, right? If somebody says you owe me money and that's a false statement, false is the one we want there. False is the good one in that case about owing somebody money. So true and false don't have any quality to them themselves. They're just a fact sort of thing. Kind of like on and off. It's just a state of things. And let's compare that to our math example there. So our original premise, x equals y and y equals z. We negate that to make it out of our conclusion. X does not equal y and y does not equal z. In our original conclusion of x equals y, or sorry, x equals z becomes x does not equal z. And now we can check the conclusion here. I'm going to put this in words and slip away from our math terms for a second to help this make more sense. So if x and z are different numbers, those are definitely different numbers. That's our starting point, the one we know for certain. For instance, taking a fact, the observation we can make. So we know for certain those are different numbers, and that means we'll never find a third number that's equal to both of them. If those are two completely separate numbers, there's a bunch of static on there. Is somebody trying to ask a question? It sounds like a blown microphone. Oh, I guess not. I don't see anything lighting. I don't see anything lighting up. I was hearing something that sounded like a blown microphone, where it's just all static coming through. If you were trying to ask a question in the chat, I am keeping an eye on the chat room here, so you can put it in there. So yeah, if those are different numbers, then we will never be able to find one number that's the same as both of them. They're different to begin with. Inequality translates through just like equality. So again, we can be certain about that that's a true statement. Thinking that this one was a true statement. So in that general sense on logic, that's provides us a way to check things, which when it comes to programming, it'll be well after school before you ever hit a problem you have to do a complicated test like this on to confirm things. Everything in school is designed to fit in our time constraints of a classroom, right? We're under tight time constraints for all our classes, so programming questions and technology questions can only get so difficult in a classroom. Otherwise, we completely run out of time and miss other things that would be important to learn. So this check won't necessarily show up in technology stuff, but it could definitely be helpful in your English classes on your way through school, and possibly on your math classes if you do have to do some proofwriting and stuff to check your logic and confirm things. If you're not sure, it gives a check, because the Contra Positive has the same truth value as the statement. Which also means they're almost interchangeable, right? We could start with the Contra Positive, and if we negate both of them and switch the order, we get back to a logical statement. So those two are almost interchangeable. It doesn't really matter which one we start with. If we go through this process, we'll get something that ends with the same truth value. But if we just negate them, and kind of same thing, if we just negated this one and kept it in this order, we'd have need an umbrella leads to the conclusion of it's raining, but that's essentially what we had here. Needing an umbrella does not necessarily mean it's raining. We need to know more details. Because rain isn't the only reason we would need an umbrella, but it's one of them. So not needing an umbrella is our premise, then not raining is a conclusion that we can draw from that. So it gives us that check. And obviously you have to do this along the way. So we can, anytime we have a logical statement, which the most useful place for this is going to be when you write essays. And you have claims that you're trying to support, and you want to make sure your support is very sound and organized and everything. You're certain about what the things you're saying. If you want to confirm it, break it down to your premise and conclusion and negate both of them. And if you end up with something that you don't really have enough details for, like you need to add details to really determine whether that's true or false, that's a good sign because it's a converse. And then switch the order, and you should have something that has the exact same truth value as what you started with. The logical statement and contra positive will always share a truth value. If we start with true, the contra positive will be true. If we start with false, the contra positive will be false. And the converse will always require details. So I guess another one, these would be true or false in a general sense. But if we need to start filling in details to get true or false on that middle step, then the logic checks out. If it follows that pattern, which is an easy pattern to follow, right? If we're talking about like an English essay, we can just think about the words backwards in our head and confirm that they make sense when negated and switching the order. It provides a logic, a check for the logic, that confirmation of certainty. We know what we're doing. And it can be helpful with programming, but really situations where you would need to check your logic like that aren't going to show up in a classroom. So more useful in like math and English and philosophy classes or ethics. Most degrees require some humanities credits, so philosophy or ethics or whichever one you choose there. You'll probably have to put some logical claims together, and having a way to check that can be really useful. But for us in general, now back to our thing in technology, as it will show up in classrooms, programmers and software developers, the other label on our course here, but also into other IT, because I just mentioned logic shows up everywhere. That's a word that applies to all of our fields in that, with that general definition we gave earlier. And in our modern world, all of those fields are going to use technology. So IT people, we tie those disparities. The disparities are in the details. Why logic seems different in English class than it does in math class, it's just the fine details. It's still a premise that results in or leads to a conclusion. So we need to, as tech people, we have to break through those disparities and the details and tie the two together. So more specifically, another example I need to put up here on the board is, okay, if I erase this, everybody who was taking notes, get that added or get a screenshot taken. I probably should have mentioned the screenshot before I stepped out of the way. If you're going to do that, there we go. That'll give time to take a picture. But just to check, and the idea of what logic is, that certainty in our truth, the truth value. It's not our point on a debate, right? It's not another issue, another detail to throw into a debate. It's the points we are absolutely certain about. And there's no more debating them.
Yep, that's what's great about logic. No debate. As soon as there's a premise and a conclusion, whether it's a true or false value, it's it's final.
Exactly. Which is why it showed up in that Star Trek example the way it did. Because Spock was always using that as a correction for when people weren't, when people were doing things that would have been up for debate. Spock was there to quickly correct them with what the logical solution was.
And also he brought the facts too. Logic isn't just about a premise, it's about a factual statement.
Exactly.
It's about a statement, whether it be true or not, actually, like you said, it could be not fact, but it's a statement.
Which is why it ties into the technology, because the machines need certain things. Machines,
they need statements, they need key phrases, keywords
stuff. They need the certainty.
Yeah,
so
they need
people have to tie logic together across the various fields.
And what's great about logic is that it's it can be applied outside of just computers. It's something you take with you for the rest of your life, and so it's very valuable to be logical and to understand that what statements that you state
is knowing when to use it, right? Like I just talked about that check on certainty, and that's going to work anywhere, but it would be very illogical to use that in a heated argument with your significant other, right?
Exactly. But it's important to have,
even though that confirmation would still apply.
Yeah, it's important to have it at the right times. And so, logic is not used in every part of computer programming. It's not used in every single aspect, since just like you said, I meant just like you said about the spouse thing, it's like there are some things where you program
for a machine, Keegan, it is. That's why we have
for machine. That's what's different.
Can only follow those certainties. So, and what we do is IT people have to tie the logic together with the various fields. So what I have in my notes here, well, we saw the other day, we finished up our lecture on that, or sort of a 3-part lecture. Our machine does math, right? The machine follows patterns, and humans made sense of that pattern and turned that back into mathematics. The machine just follows a pattern. It doesn't know what it's doing, but we'll state it this way. We'll say the machine does math, but the user, if the user is like an average person, they don't do math, right? They don't even want that math answered. They understand the linguistic or philosophical version. Not just the answer, input and output. This is what the human needs. This is what the human needs, and this is what the machine does. So we have to tie those together. So to finish up this little section, an example of tying those two examples we've been using together, and to see what this is leading into. So this is directly to the point you were just talking about, Keegan. So I'm going to set it up like pseudocode and throw a couple numbers up here. So let's set up a variable called threshold, and we'll set it at 35%, which percent's just easy to say. which is one of those linguistic things, right? The human's going to say 35%, but when we take that to a calculator, we actually type in 0.
Yeah, the technology, computers can't say it. You have to direct it to, say it, or,
So we're the ones
project it
that
in
have to
front
do
of your
that.
eyes.
We're the ones that have to do all of that. We set up another variable called chance. Well, I'm not really sure exactly where to look for this, but I'll start typing or writing up here. I'm quite certain we can go to the nws.gov, nationalweatherservice.gov, and somewhere on that page is the chance of rain, right? I don't know the exact URL for the chance of rain at this particular moment at a given latitude and longitude, but I am quite certain that the National Weather Service website it's somewhere on their page. So that's a place we could grab it. So we could get that number. And then we do that translation. The machine does the math. So like we saw the other day, we can make choices. We can ask those yes or no questions. Like, is the chance bigger than the threshold? Which again, we're not asking the machine to do that. We're telling the machine to do that. So not instead of is the question, we say if that's a true statement. So into the premise thing. So if this is a true premise, then the conclusion, what should I write here? I wrote Polly in the notes. I'll just say speaker. I was putting the notes together. I just jotted down Polly because I was doing stuff on Polly the other day. That's Alexa's voice, if you weren't familiar with that. The actual programming libraries that we use for Alexa's voice are Polly, and I wrote that in my notes. So I'm going to say speaker. That'll work. Speaker, whatever our smart speaker is. There's lots of different ones, right? I have the Google Assistant or Google Speaker, Alexa and Siri and all sorts. Now there's some generic brands starting to come out. But whichever one, if this statement is true, we just pick an arbitrary threshold, check this website for what the current chance of rain is, then have the speaker say something like, don't forget your umbrella. Otherwise, so our keyword is typically else or something along there. Otherwise, the speaker will say, speaker says, enjoy the nice weather. What I put in my notes. And if this is making you wonder, because everything we're looking at this semester, we do text-based output. Those smart speakers do take that text-based output. They read our language. So as far as printing the output, to send it to the smart speaker is exactly the same as to send it to the console, like we've been doing in our examples here. We just put together the sentence and takes a little bit more if we want to expand that and add some emphasis and stuff, or make the smart speaker trick another human into thinking it's a human and not a computer. There's a great example of that. I'll pull up here in just a second. But does that make sense? Tying our logic back into what we were doing. So all those logical statements we were just looking at. There's that math part. Now,
could you do the contra positive of that?
so the contra positive will negate both of them If negate both of them and switch the order. So if, actually, I'll do it in a couple steps. There's a couple things we can do. So negate both of them, we can put it in here and switch the order. I erased it, I already forgot what I had. Did I have chance less than threshold?
You had chance equals, yeah, less than threshold. Speaker says, don't forget your umbrella.
Okay, so switching the order, and I'm gonna abbreviate that word, would be threshold bigger than chance. Whoops. So that switch the order, and then I just put a not out front to negate everything. And then in this case, we can take that not and apply it to our inequality operator, right? It's not greater than would be less than or equal to. Did I do that backwards? I think I did that backwards. Our original one was this, right? If chance is bigger than threshold. So switching the order, we turn that around.
Your original said chance, chance was on the left, threshold was on the right.
Yeah,
From my
sorry,
notes.
I confused myself. Let me go
No,
back.
it's okay.
So chance is bigger than threshold. That's the one that we should need an umbrella for, right? If our chance of rain is 50% and our threshold is only 35%, we should have our umbrella. So then to negate it, we put a not out front. And then we can apply not to the operator here. So not greater than would be less than or equal. So if chance is less than or equal to threshold, so 20% chance, 34% chance, 35% chance, we might still want our umbrella, right? We need those details. So there's our converse. And when we switch the order, we can do that quickly just with the symbol here. We get back to if chance is greater than or equal to threshold, which 50% chance, 70% chance of rain. We probably want our umbrella. Does that make sense, Tyler?
Yeah.
Okay. And yeah, even on a simple case like that, I confused myself while I was talking and doing it at the same time.
I feel like another workspace would have helped you there. How you got limited by your space.
Yeah. There's it can be a little confusing even in simple situations to thinking that through, or I think what happened there was the traditional way to say it is walk and chew gum at the same time. I was trying to do two different things at once and got a little off. But the contra positive is still the same. And when we had that converse along the way, we didn't have enough details. So that is a constant in logic when we apply these things. And that's why we need to study it, because our machines do the math sort of logic. But our users, they need the English sort of logic. So we're the ones that tie it together. We have to bring those two pieces together, and that way the user gets what they need from an automated process. That's why we're studying logic. Let's see, what time is it? 2:05. So we have just enough time to look at this example, because, well, for that generic example, I was talking about a smart speaker, right? I guess there'd probably be another condition here. if chance is bigger than threshold, or in this case, we'd say if chance is at least the threshold, so anything 35% or above, and the user is heading out the door, right? Maybe have a motion sensor there by the front door, so that as the human starts to walk out the door, the speaker's like, oh, don't forget your umbrella, it's going to rain. Set up something like that. And like I said, the to print out the words is straightforward like that. It's exactly like printing to a console. We just type the words we want to print at, we want the speaker to say, and then everything else is already pre-built for us up to the point of just spitting them out. That would sound like a machine. There's another step that's a little bit better, and I thought this was really interesting. So let me see if I can find the video real quick. Oh, I've stopped screen share. Did I share my sound? Share the sound, that way you can hear the video, because it is it's about smart speakers, so it's a very important one. I do this a link to it. Google Assistant. Schedule hair appointment. Yeah, right at the top. So this was from Google's most recent conference.
Ad-free, secure email for teams of all sizes.
Sorry.
Meet Zoho
Yes.
Mail.
2 for $6 for you, from us, for real.
The progress with the assistant. As I said earlier, our vision for our assistant is to help you get things done. It turns out a big part of getting things done is making a phone call. You may want to get an oil change schedule, maybe call a plumber in the middle of the week, or even schedule a haircut appointment. You know, we are working hard to help users through those moments. We want to connect users to businesses in a good way. Businesses actually rely a lot on this, but even in the US.
Okay, so what he just mentioned there is the point of this, in a good way, right? We've, yeah, here in April of 2022, I'm going to go ahead and feel it's safe to assume that everybody has dealt with the chat bots and the automated voice call things and navigating your way through a menu to get to an actual human that can help you, right? And we know the difference between the automatic systems and the humans.
60% of small businesses don't have an online booking system set up. We think AI can help with this problem. So let's go back to this example. Let's say you want to ask Google to make you a haircut appointment on Tuesday between 10 and noon. What happens is the Google Assistant makes the call seamlessly in the background for you. So what you're going to hear is the Google Assistant actually calling a real salon to schedule the appointment for you. Let's listen.
So how can I help you?
Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd.
Sure, give me 1 second. Sure, what time are you looking for around?
At 12 p.m.
We do not have a 12 p.m. available. The closest we have to that is a 1:15.
Do you have anything between 10 a.m. and 12 p.m.?
Depending on what service she would like. What service is she looking for?
Just a woman's haircut for now.
Okay, we have a 10 o'clock.
10 a.m. is fine.
Okay, what's her first name?
The first name is Lisa.
Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd.
Okay, great. Thanks.
Great. Have a great day. Bye.
So it goes on for a minute after that. There's some more examples, but the basic idea there is that doesn't really sound like a machine anymore, right? They did lots and lots of those tests, obviously, debugging their software, and the latest versions of those are consistently fooling humans. They think they're talking to another human. Really, it's the size and the grunts thrown in there, and then the tone of voice starts to seem a little annoyed when things aren't working out. I just wanted to share that because I thought that was really neat with the AI stuff. And the latest versions are consistently fooling humans about whether they're talking to a human or a machine, if it's not right there to see it. So a big step forward. So that's a little bit more than just printing out the words, but all of that stuff is made. It's pre-built. It's like those tools when we write our program, right? When we go to write a program in Python, if we need to get some input from user, we just use that keyword input and throw up a prompt, and that pre-built part is already there. We don't have to worry about it or anything. It's actually a concept called encapsulation that will be a big deal later in your studies, so might as well preview that word. We don't have to worry about it. We know it works. We know it's going to do what it's supposed to do, and we just use it. And same thing on those advanced systems where those automated systems are fooling humans now as to whether or not they're talking to a human or an automatic system. That stuff is built, it's ready. So as programmers, we'll use that the same. And for our part, it's like the input function in Python. It's already built. We know it's there, so all we do is ask it to run, and it does its thing automatically for us. So that is something that you will see, that you will certainly see in your programming, because that makes for much better output than black words on a white screen, right? Or white words on a black screen. I guess that's what our homework assignments, how our homework assignments color it. But we can do much better, and that stuff's already made for us. So just like the input function in Python, all we have to do is ask for it. We don't have to do a lot of fancy parts. But I wanted to, that example is from fairly recently, and it seemed to lead naturally from where the logic thing ended. There's a little bit more to talk about logic, about how I said it was, I mentioned back on page 1 of my notes, so it was a while ago, about we can build mathematics from it, from logic. All of Boolean algebra, which predates computers as we know them. So we still need to talk about that, but we did a whole lot of talking Monday, so I assume you all are probably ready to actively do something. So I'm going to push the other half of the talking about logic part back to Monday, and then we have do an actively do an example, actively do something. But first, probably a good time to take a break, right? Does 10 minutes sound good to everybody?
Yep, sounds good. Especially with the rain outside. It's very, energy is very low for me.
Yeah. I usually drink a half a Mountain Dew before a lecture, and I drank a whole Mountain Dew today. So that happens to everybody. Kind of relates to our logical statement we were looking at, because we can almost say that about all people. When it starts raining, our energy level goes down. But it's 2:13, so we'll get back to it at 2:23 and look at random numbers, and then we'll do a deck of cards example for random numbers. So I'll see y'all here in just a few minutes.
All right, sounds good.